Everything's bigger in Texas, but these mega projects take it to an entirely new level. From multi-billion-dollar highways to massive industrial zones reshaping entire regions, the Lone Star State has built faster and larger than ever before. Today we reveal the biggest mega projects in Texas and the jaw-dropping scale of what it really means to innovate in America. The Port Arthur LNG project is a large-scale liquefied natural gas development located along the Gulf Coast of Texas. This mega project, envisioned as a major export facility, encompasses multiple phases of complex engineering and construction efforts aimed at transforming raw natural gas into a liquefied state for overseas shipment. The process begins with site preparation, involving extensive clearing, grading, and compaction of coastal terrain to accommodate heavy infrastructure while ensuring stability against flood and storm surge risks common to the region. Soil stabilization techniques, including deep soil mixing and surcharge preloading, are employed to enhance bearing capacity for future foundation loads. Following site readiness, pile driving operations commence to support the foundations of cryogenic storage tanks, compression stations, and liquefaction units. These piles, typically made of steel or pre-stressed concrete, are driven deep into the subsurface to anchor against settlement and seismic activity. Simultaneously, massive underground utility corridors are excavated to house process piping, electrical conduits, and stormwater management systems. A key engineering challenge lies in the routing of high-pressure pipelines feeding the liquefaction trains, which must be precisely aligned and welded under strict tolerances to prevent leaks and ensure continuous flow. The core of the facility is composed of liquefaction trains, each comprising heat exchangers, compressors, gas turbines, and associated cooling systems. These units transform natural gas into LNG by progressively lowering its temperature to approximately minus 162 degrees Celsius. Modular construction techniques are often employed to fabricate components off-site and ship them to Port Arthur, where they are lifted into place using high-capacity cranes. This approach accelerates assembly and minimizes labor-intensive on-site fabrication. Adjacent to the process area, full containment LNG storage tanks are erected using a combination of pre-stressed concrete outer walls and inner nickel-steel liners. These tanks require precise thermal insulation layers and boil-off gas recovery systems to manage pressure buildup. Marine infrastructure, including berths, jetties, and loading arms, is constructed along the shoreline to accommodate LNG carriers. This involves extensive dredging, pile-supported dock structures, and mooring systems designed to handle the thermal contraction of cryogenic loading arms. The project integrates advanced safety systems such as gas detection, emergency shutdown valves, and fire suppression networks. Electrical power distribution is established through substations and redundant backup generators, ensuring operational reliability. Finally, commissioning and startup testing involves systematic validation of all mechanical, electrical, and control systems before the terminal is certified for commercial export operations. The Bay City Green Hydrogen Plant is an advanced industrial facility designed to produce hydrogen using electrolysis powered by renewable energy sources, primarily solar and wind. Situated in proximity to both energy supply corridors and industrial hydrogen demand centers, the project begins with extensive land development, which includes grading, drainage design, and geotechnical stabilization to support heavy equipment loads and ensure safe operation under varying environmental conditions. Electrical grounding systems are embedded in the foundational layout to protect sensitive electrolysis components from surges and lightning. Once the site is cleared and compacted, construction of the primary electrolysis units begins. These systems, typically using proton exchange membrane or alkaline electrolyzer stacks, require a precise mechanical and electrical assembly environment. Prefabricated skid-mounted modules are delivered to the site, each containing electrolyzer cells, transformers, rectifiers, and water purification units. These modules are set on reinforced concrete pads with embedded anchor bolts to withstand thermal cycling and mechanical vibrations. Deionized water feed systems are installed, incorporating reverse osmosis and filtration units to ensure electrolyte purity, which is critical for electrolyzer efficiency and longevity. Adjacent to the electrolyzers, a high-voltage substation is constructed to interface with renewable energy sources. This substation steps down incoming electricity from transmission voltages to operational levels suitable for the direct current systems feeding the electrolysis stacks. Power distribution infrastructure includes underground cable trays, switchgear enclosures, and load centers with automated fault detection. Battery energy storage systems are often co-located to buffer intermittent generation from renewables, smoothing out power supply fluctuations to maintain consistent hydrogen output. Hydrogen produced on-site is directed through stainless steel piping systems to compression units where it is pressurized for storage or distribution. These compressors are housed within sound-attenuated enclosures to meet regulatory noise limits and are equipped with redundant safety valves and blowdown stacks. Storage vessels, typically cylindrical tanks rated for several hundred bar, are constructed using high-strength carbon steel alloys and are fitted with pressure and temperature monitoring instrumentation. A control center oversees plant operations via a distributed control system that integrates sensors, flow meters, and programmable logic controllers. Real-time data acquisition enables operators to optimize electrolysis efficiency and respond to any anomalies. The plant also incorporates emergency shutdown systems, gas leak detection, and fire suppression equipment to meet industrial safety standards. Upon completion, commissioning involves a phased startup of each system, pressure testing of gas lines, calibration of instrumentation, and validation of control logic before the plant is cleared for continuous green hydrogen production. The Southeast Connector project in the Dallas-Fort Worth region is a significant transportation infrastructure initiative designed to expand and modernize a key highway corridor to accommodate increasing traffic volumes and improve regional mobility. The construction process begins with detailed geotechnical investigations to assess subsurface conditions across the route. Boreholes and soil sampling guide the design of pavement structures and inform decisions about embankment stabilization, especially in areas with expansive clay or soft subgrades. Initial site work involves extensive utility coordination and relocation, given the presence of underground power lines, fiber optics, gas mains, and municipal water systems. Specialized crews use hydro-excavation and trenchless boring methods to install new utility runs without disrupting surface operations. Simultaneously, the construction zone is cleared of vegetation, existing pavement is milled or demolished, and temporary drainage measures are installed to manage stormwater during earthworks. Mass grading operations utilize GPS-guided bulldozers and scrapers to sculpt new roadway alignments, build embankments, and excavate cut sections through rolling terrain. In low-lying areas, wick drains and surcharge fills are employed to accelerate settlement and enhance long-term subgrade stability. Reinforced concrete box culverts and precast arch structures are installed to span creeks and drainage channels, with erosion control mats and riprap protection placed at inlets and outlets. The highway widening includes adding general-purpose lanes and managed lanes, which requires staged construction to maintain traffic flow. Temporary detours and traffic control devices are deployed in phases, with barrier systems, message boards, and flagging operations ensuring worker safety. Sub-base materials such as lime-treated soil or cement-stabilized base are placed and compacted before successive layers of hot-mix asphalt or continuously reinforced concrete pavement are applied. Bridges along the corridor are demolished and reconstructed with wider spans and higher clearances to meet modern standards. Foundation construction includes driven steel H-piles or drilled shafts depending on soil conditions, followed by the erection of cast-in-place or precast concrete bridge components such as abutments, piers, and girders. Superstructure placement is often conducted during overnight closures to limit traffic disruptions. Sound walls, intelligent transportation systems, lighting, and signage are installed in parallel with the mainline construction. Dynamic message signs, vehicle detection loops, and closed-circuit cameras are connected through fiber optic networks to regional traffic management centers. Upon completion of paving and striping, punch list activities address final grading, landscaping, and system testing before the project is opened fully to public use, significantly enhancing connectivity between southeastern Dallas and central Fort Worth. Rising prominently over the Corpus Christi Ship Channel, the Harbor Bridge Replacement Project represents a transformative upgrade to the region's transportation and maritime infrastructure. The effort to construct the new bridge begins with significant preparatory work, including clearing, grading, and establishing access roads for heavy machinery. Crews undertake extensive geotechnical surveys to design deep foundation systems that can safely support the towering cable-stayed structure in a coastal environment prone to high winds, corrosive salt air, and variable soil conditions. The core of the construction involves the installation of massive drilled shaft foundations. These are created using rotary rigs that bore deep into the substrata, often through layers of clay, sand, and limestone. Reinforcing steel cages are then lowered into the shafts and encased in concrete to form durable vertical supports. Given the location over navigable waters, temporary work platforms and marine barges are mobilized to provide access and material staging for overwater operations. The centerpiece of the bridge consists of two towering pylons that anchor the cable-stayed design. These pylons are constructed incrementally using a climbing formwork system that allows each concrete lift to cure before the next section is poured. Precision alignment is essential as the pylons must remain perfectly vertical over hundreds of feet of elevation. Once the pylons reach their full height, installation of the stay cables begins. These high-tension steel cables are anchored at the pylons and radiate outward in a fan-like array to support precast bridge deck segments. Deck segments are installed using a balanced cantilever method, where sections are added symmetrically from both sides of the pylon to maintain structural equilibrium. Each segment is carefully aligned and post-tensioned into place, forming the long-span roadway over the ship channel. Throughout this process, real-time structural health monitoring systems are employed to measure stress, displacement, and vibration to ensure safety and integrity during construction. The bridge approaches are constructed concurrently, involving the erection of elevated spans supported by precast concrete girders and pier caps. These components are assembled using cranes and falsework, followed by placement of the riding surface and expansion joints. The project also includes roadway realignments, upgraded interchanges, and the integration of pedestrian and bike paths to enhance multimodal accessibility. Upon completion, extensive commissioning activities verify all structural, electrical, and drainage systems. The new harbor bridge will provide significantly improved clearance for maritime traffic, greater traffic capacity for vehicles, and enhanced resilience against hurricanes and seismic events, marking a new chapter in regional infrastructure advancement. At the heart of downtown Austin, the Texas Capitol Complex Phase 2 represents a continuation of a multi-year development plan to expand and modernize state government infrastructure while respecting historical context. Construction activities begin with meticulous site logistics planning to accommodate the urban setting, including traffic control, pedestrian rerouting, and staging areas for heavy equipment within a dense government district. Selective demolition of outdated facilities and parking structures clears the way for excavation, utility relocation, and deep foundation work. Excavation reaches depths sufficient for multi-level underground parking and utility corridors. During this phase, crews deploy soil shoring systems using soldier piles and lagging or secant wall methods to ensure trench stability and protect adjacent buildings from settlement or vibration. Dewatering systems with sump pumps and well points are installed to maintain dry conditions during substructure construction. Concurrently, new utility infrastructure, chilled water lines, electric duct banks, and storm drainage systems are embedded in concrete-encased trenches. Structural concrete operations dominate the next phase, with mat foundations poured in multiple continuous placements to support new office towers. Tower cranes are erected early to facilitate vertical construction, hoisting rebar bundles, formwork panels, and precast components. Floor slabs are formed using a combination of post-tensioned and reinforced concrete techniques to optimize span lengths and reduce floor thickness. Core walls housing elevators, stairwells, and mechanical shafts are formed with slip-form systems to accelerate vertical progress while maintaining structural alignment. Above grade, architectural precast concrete panels are installed as part of the building envelope. These panels incorporate design motifs inspired by the adjacent capital and blend with the surrounding architectural aesthetic. Window systems include energy-efficient glazing and aluminum framing with integrated sunshades. Mechanical, electrical, and plumbing systems are integrated into each floor through overhead coordination with BIM modeling to avoid clashes and maximize efficiency in confined ceiling spaces. A key element of the project is the expansion of the Texas Capitol Mall, which introduces pedestrian green space atop underground parking decks. This requires careful waterproofing, drainage layering, and placement of structural soil to support landscaping elements. Trees, lighting, benches, and pathways are installed using detailed site plans to ensure ADA compliance and long-term durability. Interior finishes follow close behind structural completion, including raised flooring for cabling flexibility, modular wall systems, acoustic ceiling panels, and high-efficiency HVAC controls. Security systems, IT infrastructure, and life safety features are tested during commissioning. When completed, Phase 2 adds critical state office space, enhances connectivity through walkable corridors, and reinforces the ceremonial axis of the Capitol with modern construction methods and sustainable design. Serving as one of the largest and busiest airports in the world, the Dallas-Fort Worth International Airport represents a vast and intricately planned transportation infrastructure. The original construction of the airport began with the selection and preparation of an expansive site straddling the cities of Dallas and Fort Worth, requiring extensive grading, drainage systems, and soil stabilization over thousands of acres. Earth-moving operations included the redistribution of millions of cubic yards of soil to establish level runways, taxiways, and terminal zones, while ensuring compliance with strict FAA airfield geometry standards. The runways, which are among the longest in the country, were constructed in multiple phases using layered pavement systems. These include a stabilized subgrade, cement-treated base, and several layers of high-performance concrete capable of withstanding repeated heavy aircraft loads. Each runway incorporates lighting systems embedded in the pavement for approach, edge, and touchdown guidance, connected via underground conduits to airfield lighting control stations. Parallel taxiways are designed for optimal aircraft movement efficiency, with concrete paving sections built using slip-form pavers for tight tolerances and surface uniformity. Terminal construction involved erecting multiple large-scale structures with steel-framed superstructures and curtain wall systems composed of aluminum and high-efficiency glazing. Each terminal is equipped with multiple gate positions, connected to jet bridges, and supported by mechanical systems such as baggage handling conveyors, passenger boarding controls, and HVAC systems designed for high occupancy and variable loads. Subsurface utilities and automated train tunnels were constructed simultaneously, using cut-and-cover and bored tunneling methods to ensure interterminal connectivity without interrupting aircraft operations. The airport includes a central utility plant, constructed with chillers, boilers, and thermal energy storage tanks to provide efficient heating and cooling across the entire complex. Electrical substations and emergency backup generators are integrated into the system for uninterrupted power supply to critical operations such as runway lights, security systems, and air traffic control. To support intermodal transport, extensive roadways, bridges, and parking structures were built using pre-stressed concrete beams and deck slabs. Toll plazas and access control points are integrated with ITS systems for real-time monitoring and traffic regulation. Continuous expansion projects include terminal upgrades, runway extensions, and the integration of sustainability features such as solar panels, stormwater retention basins, and energy-efficient lighting. From a construction and engineering standpoint, Dallas CU-Fort Worth International Airport is a constantly evolving megastructure requiring phased construction strategies, airside-landside coordination, and specialized materials and systems to support safe and efficient global aviation operations. Towering above one of the busiest highway corridors in North Texas, the High-5 Interchange in Dallas stands as a hallmark of multi-level interchange engineering. Built to replace a congested cloverleaf interchange where U.S. Highway 75 intersects with Interstate 635, the project required innovative design and construction techniques to manage complex traffic patterns while maintaining continuous vehicle flow through one of the region's primary transportation arteries. Initial phases began with detailed traffic modeling, utility mapping, and soil investigations to support the five-tiered structure's foundation. Given the depth of the lower roadways and the height of the upper ramps, foundation construction included the use of deep drilled shafts extending over 100 feet into the ground. These shafts were reinforced with heavy rebar cages and cast with high-strength concrete to support the significant vertical and lateral loads imposed by tall piers and long-span bridge decks. The interchange's construction was sequenced using a segmental approach, allowing multiple elevated ramps to be built concurrently with minimal interference to active lanes below. Crews used massive cranes to place precast concrete segments and steel girders at heights reaching over 120 feet. False work towers and temporary supports were utilized extensively to hold bridge components in place until post-tensioning systems were installed to lock the segments into structural integrity. Each level of the interchange demanded precise vertical and horizontal alignment, especially in the curved flyover ramps that must safely accommodate high-speed traffic. Bridge decks were formed using steel-reinforced concrete with epoxy-coated rebar to enhance corrosion resistance, an essential consideration in a structure exposed to both descent salts and Texas heat. Expansion joints, drainage inlets, and safety barriers were integrated during deck placement to ensure long-term durability and operational safety. Utility coordination was a major undertaking as numerous fiber optic lines, water mains, and gas lines crossed the construction zone. Relocation efforts required directional drilling, jack and bore methods, and trench excavation under tightly managed shutdown windows. In parallel, intelligent transportation systems were embedded, including dynamic signage, surveillance cameras, and real-time traffic sensors networked to regional control centers. Lighting, landscaping, and architectural detailing followed structural completion, contributing to the interchange's distinct urban identity. At full build-out, the High-5 interchange improved traffic capacity, reduced weaving conflicts, and significantly enhanced mobility for both regional and local drivers, all achieved through precise civil engineering, rigorous construction phasing, and innovative use of vertical space. Situated in the heart of Southeast Texas's industrial corridor, the Golden Triangle Polymers project represents a major advancement in the Gulf Coast's petrochemical manufacturing capacity. This massive facility is being constructed to produce polyethylene and other polymer products from ethylene feedstock derived from natural gas liquids. The project begins with the development of a multi-acre greenfield site, requiring extensive earthwork, drainage management, and foundation preparation across terrain with high groundwater and soft, compressible soils. Soil stabilization techniques include the use of lime or cement treatment and surcharge fills to achieve acceptable bearing capacities for large process structures. Deep foundation systems are essential to support the heavy loads imposed by vertical vessels, reactor units, and compressor modules. Construction crews install drilled piers and driven piles to depths exceeding 100 feet, with precision tolerances ensured through the use of GPS-guided rig systems and real-time monitoring during installation. Once foundations are completed, concrete pads and structural steel framing are erected to house process units such as cracking furnaces, separation columns, and polymerization reactors. These are built using modularized construction strategies, where large components are fabricated off-site, shipped by barge or heavy-haul truck, and lifted into position by crawler cranes with lifting capacities over 1,000 tons. The core production process centers around the ethane cracking furnaces, which convert ethane into ethylene through high-temperature thermal decomposition. These furnaces are complex assemblies of fireboxes, radiant tubes, and convection sections, all requiring precise refractory lining and thermal insulation. The resulting ethylene gas is rapidly quenched and routed to distillation columns where it is separated from byproducts under carefully controlled pressures and temperatures. Polymerization units downstream transform ethylene into polyethylene pellets through catalyst-induced chain reactions inside high-pressure reactors. These areas are designed with extensive piping, instrumentation, and control systems to maintain strict process parameters. Each reactor line is supported by a network of utility systems, including nitrogen generation, compressed air, cooling water, and steam distribution, all interconnected through color-coded pipe racks spanning hundreds of feet. Electrical power for the facility is delivered via high-voltage substations and switchgear buildings, incorporating redundant feeds and uninterruptible power supplies for critical control and safety systems. Distributed control systems and programmable logic controllers operate from a central control room, managing process sequencing, alarms, and interlocks. Fiber optic networks connect instrumentation throughout the site to provide real-time monitoring and diagnostic capabilities. A significant part of the construction effort is dedicated to environmental compliance and emissions control. Flare systems, vapor recovery units, and wastewater treatment plants are installed to capture and process effluents, ensuring the plant meets federal and state environmental standards. Additionally, fire protection systems, including foam suppression, hydrants, and emergency deluge zones, are integrated throughout the site to mitigate risks associated with flammable materials. Upon completion, commissioning and startup procedures involve comprehensive testing of mechanical systems, loop checks of instrumentation, safety interlock validation, and initial product runs under controlled conditions. The Golden Triangle Polymers project, once operational, will stand as a cornerstone in the region's industrial landscape, combining large-scale chemical engineering with advanced construction practices and operational precision. Stretching across the coastal plains of Kennedy County, Texas, the Penascal Wind Power Project showcases the application of large-scale renewable energy infrastructure in a challenging environment defined by soft soils, high humidity, and persistent coastal winds. The construction process begins with extensive site development, including topographical surveys, environmental assessments, and access road construction through otherwise undeveloped ranch land. These gravel roads must support the transport of extremely long turbine blades, tower sections, and nacelles, necessitating careful grading, compacted subbases, and wide turning radii for specialized transport vehicles. One of the primary engineering tasks in this project involves the foundation work for each wind turbine. The coastal soil profile, composed largely of silts and clays with varying moisture content, demands a foundation solution capable of resisting both vertical dead loads and dynamic overturning forces induced by wind. Each turbine foundation typically consists of a large circular reinforced concrete pad, often exceeding 50 feet in diameter and several feet thick, with a central pedestal rising above grade. The foundation is constructed after excavation, followed by rebar cage placement, anchor bolt installation, and a continuous concrete pour to ensure uniform curing and structural integrity. The turbine towers are delivered in multiple tubular steel sections, which are bolted together on-site using tensioned bolts and high-strength flanges. Erection is carried out using hydraulic or lattice boom cranes with lift capacities tailored to the height and mass of each tower segment. Each tower supports a nacelle, a housing unit for the generator, gearbox, and control electronics, which is lifted and mounted at heights reaching over 200 feet. Rotor assembly involves attaching 3 fiberglass reinforced blades to a central hub on the ground, then lifting the entire rotor assembly as a single unit and mating it with the nacelle. Electrical infrastructure includes the installation of underground medium voltage collection lines connecting each turbine to an on-site substation. These cables are buried in trenches with warning tape and sand bedding to prevent damage and ensure thermal dissipation. The substation steps up the voltage from around 34.5 kilovolts to transmission levels, often around 138 kilovolts, for integration into the regional grid. Control buildings house switchgear, protection relays, and SCADA systems that allow for remote monitoring and turbine control. Given the site's proximity to the Gulf of Mexico, the project incorporates several measures for corrosion resistance, including galvanization of structural steel, marine-grade coatings on exposed equipment, and sealed electrical enclosures. Turbines are fitted with lightning protection systems that channel electrical discharge safely to ground, a critical feature in a region prone to frequent thunderstorms. Operational testing involves synchronization of the turbines to the grid, blade pitch calibration, yaw system checks, and vibration analysis to ensure balanced rotation. Once commissioned, the Peñascal wind power project contributes hundreds of megawatts of clean energy, capitalizing on the consistent wind resources of the South Texas coastline, while demonstrating advanced construction sequencing and logistical planning in renewable energy deployment.